Okay, thank you. I'm going to use a microphone because I'm losing my voice. Yeah, so thanks for being here for the last talk, which I guess it's been probably a long 2 weeks or whatnot. So in this second half, I'm going to talk more about what we've actually observed from fast radio bursts. Obviously, yesterday I was trying to emphasize how we go about detecting these things in the first place, but now I'm going to talk about a bit more what we've actually seen so far from these sources, and hopefully yesterday's lecture will give you a bit of insight into how we actually make these measurements. I saw that at least one person has managed to determine the dispersion measure and the rotation measure of the data that I gave you yesterday, so feel free to keep working on that if you want, and send me questions by email if you have any. So to kind of bracket this talk, I figured I would start by mentioning gamma ray bursts, and the fact that gamma ray bursts have been very exciting sources for the last 20 years or so, because they're really pointing to the directions of extreme astrophysical events, and that has been really underlined in the last year by the direct association with a gravitational wave event as well. So you could ask the question, is it possible maybe that in other wave bands like radio, where we haven't done a very good job of exploring the sky at short time scales and looking for rare events, is it possible that we're maybe missing something that is equally as scientifically interesting by looking in the radio? And it could well be, and that FRBs are potentially showing us that there are interesting things to find in the radio as well. But I'll emphasize that if you look at a gamma ray burst, this is just an old image from one of the early gamma ray burst detections. That burst is really obvious on the sky. It's kind of as bright as the rest of the gamma ray sky combined. Lasts for a short amount of time. We're able, with gamma ray telescopes, to build all sky monitors that have sufficient sensitivity that they can pick up gamma ray bursts. We're not able to do that in the radio yet. I mean, obviously, a car antenna, you're picking up a radio station, that is basically sensitive over the entire sky, but the sensitivity of an antenna on a car is incredibly small, and you're not going to detect any astrophysical events with that. Maybe some pulses from the Crab pulsar, potentially, but you're not going to find interesting new astrophysical events. So we haven't been able to build a radio telescope yet that provides an all-sky monitor. I'll come back to that point a little bit later. And typically, radio telescopes that have sufficient sensitivity to detect pulsars or to detect fast radio bursts or other astrophysical events, they have very small fields of view. And what I'm showing here is the Parkes radio telescope. It's a 64-meter dish in Australia. The Parkes telescope has a multi-beam receiver, so it has a multi-pixel camera that allows the telescope to actually point in 13 different directions at the same time. So it has a somewhat bigger field of view than most radio telescopes, and it has a field of view that's 13 times larger than it would be if it only had a single receiver at the focus. But despite that, the field of view is still much less than a square degree, and the Parkes telescope, which has been instrumental in discovering the fast radio burst phenomena, it still takes 10 days of observing, so about 240 hours of observing to detect one single fast radio burst. So it's a huge investment to detect these signals, even with a telescope that has a nominally large field of view. And of course, compared to gamma ray bursts, as I was mentioning yesterday, the other hurdle that we have for radio detections are all these propagation effects that I was telling you about yesterday. So scattering can wash out signals at low frequencies, so it could be that our low frequency radio telescopes like LOFAR are just never going to find fast radio bursts because they're washed out by scattering. Dispersion means that we need to search over this extra parameter space to detect signals at all. And this is a hindrance. It means that we need to go to more effort to detect these sources, but it's also a help at the same time, because as we mentioned yesterday, and as I'll emphasize in some of the slides, man-made radio signals provide a background, or a foreground, I guess I should say, that we need to differentiate astrophysical sources from. So having these kind of propagation effects that we can associate with the intervening material in the interstellar medium or in the intergalactic medium is really quite helpful for determining what sources are genuinely astrophysical and which ones are man-made. So I showed you this slide yesterday. I showed you what is considered the first fast radio burst. It's called the Lorimer burst, found by Dunk Lorimer and a student in Australia. Actually, people were doing searches for short duration transients not that long after pulsars were discovered. I know that there's a paper by Stirl Finney and Joe Taylor from 1979 where they were looking for coherent emission from other things besides pulsars. So even in the 1970s, people were interested in seeing, are there other coherent emitters like pulsars that we can detect with radio telescopes. But back then, the recording bandwidth, so the available range of radio frequencies and the time resolution was quite limiting. So that's probably the reason why they were unable to detect this phenomena. What's interesting about the Lorimer burst, I'll remind you again because you're going to see lots of plots that look similar to this, that what's actually plotted here is the radio frequency on the y-axis, and on the x-axis is the time. So again, this burst shows this dispersive sweep because it's traveling through some kind of ionized material, and this is causing the signal to arrive later at lower frequencies. What was interesting about this signal was not just the fact that it has a high dispersion measure, which I'll mention again. It was also the fact that, again, because the telescope's field of view is so tiny, they observe for a couple hundred hours, and based on this detection, you can kind of infer, what would be the event rate of transients like this. If the telescope has a certain field of view, we observe for a certain amount of time, how many of these are happening if we were able to see the entire sky with the same sensitivity. And what's actually been inferred, which I think is pretty amazing, is that fast radio bursts have event rates of thousands per day. So if you have a sensitive radio telescope, if it's looking in the right direction, there are thousands of these events per day that you could detect. I've been talking for something like 5 minutes, so there's been like 50 fast radio bursts that have happened in the last 5 minutes or so, but we haven't detected any of them, as far as I know. So galactic dispersion, just reminding you again what's the main criteria for differentiating most fast radio bursts from pulsars is the fact that we use these models for the distribution of ionized material in our galaxy to predict how much dispersive delay there should be for a given line of sight and for a given distance. And you saw this yesterday, but I'll show it again because it's really a crucial point. For fast radio bursts, this particular source, looking towards the Large Magellanic Cloud, you would expect the dispersive delay across the entire band to only be as wide as that green bar, but what was actually observed requires a much larger dispersive column, and that was ascribed to the intergalactic medium, and that led to the inference that this source must be coming from a redshift of about 0.5 or so. That was controversial at the time, and it's still possible that this is highly inaccurate. But as I'll show you, we have at least one source where we have an independent determination of redshift. So if we consider these fast radio bursts in the context of other radio transients, and this is a very famous plot, or this is a version of a very famous plot that I think was first made by Jim Cordes in the early 2000s. What it's plotting essentially is a parameter space of astrophysical radio transients, and on the x-axis is essentially the width or the duration of the transient. So and it's multiplied by the observing frequency, but roughly speaking, 10 to the 0, that is at a gigahertz, that is a transient that lasts for about a second or so. And on the y-axis, we have peak luminosity. So you can see where the pulsars inhabit this diagram. Pulsars typically have pulse widths of a few milliseconds or so, and they have characteristic peak luminosities on the order of a few tens or maybe even a few hundred Jansky kiloparsec squared, which is a weird unit, but it's kind of the fiducial number for most galactic pulsars. If you look up to the green dots, these are giant pulses that we have from pulsars. We have the Crab nanosecond shots, so the Crab pulsar can produce nanosecond duration radio pulses, which have enormous peak luminosities. But the fast radio bursts, they nominally have similar durations to the radio pulsars, but much higher luminosities if you believe the redshifts that we've inferred based on dispersion measure. And these are all coherent emitters, so these are all sources where the emission process is a coherent emission process. Obviously, there are radio emitters that are incoherent emitters, like radio flare stars shown in black there, or solar flares. And this means they have high brightness temperatures. Do you guys know what brightness temperature is? It's basically the equivalent temperature for that luminosity. So we can tell that these are non-thermal processes because the brightness temperatures are absolutely insane. The crab giant pulses, for instance, the nanoshots are 10 to the 40 Kelvin or so. So it's obviously not a genuinely thermal process. So this Lorimer burst, it was very exciting. This happened roughly at the time I was finishing my PhD, about 10 years ago. And people got very excited to search for fast radio bursts and to find more examples of this phenomena. People are also skeptical, of course, because with one detection, it's unclear whether we've really found something new and interesting or whether this is just some bizarre signal. But a lot of time passed, many years passed, and no one was able to find a second example of this phenomena. And things got quite concerning. I'm going to give a little bit of a historical, tangential historical note here. A number of people were working with the Parkes radio telescope to try and find more fast radio burst sources. And one of the PhD students working on this project, Sarah Burks-Polar, she was finding some examples of apparently dispersed signals in the data set that they had. But what was strange about these signals, if you look in the top left-hand corner there, that's what the signal looks like. If you de-disperse it, you add all the frequencies together, and that's what it looks like in each of those 13 pixels I told you about that are available for the Parkes telescope. And the problem is the signal appeared in every direction that the telescope could look. And what that means is that this source must be in the near field. It's within the Fresnel distance of this telescope, so it's some local source of radio emission. There's no way an astronomical source can appear in all of the beams of the telescope. It's possible that the position of an astronomical source is in between pixels and that you might see it weakly in 2 of them or maybe weakly in 3 of them, but seeing it in every direction at the same time means that it's a near field emission. And what was concerning is, of course, if you look at what we call the dynamic spectra, by which I mean just frequency versus time, you can see three examples of this phenomena. They kind of look like fast radio bursts. They have this swept frequency emission to them, although it's a little bit strange. They have these kind of patches to them. In some cases, there's a little bit of a kink, so they don't perfectly follow the expected dispersive delay, but they certainly look a lot like fast radio bursts. So Sarah called these peritons. The idea is that this is some kind of mythological animal that casts the shadow of a man, but is actually something quite different. So these are signals that were obviously something quite different, but they certainly looked quite a lot like fast radio bursts. The only difference really was that fast radio bursts were really only seen in 1 pixel of the telescope, so they had to be coming from further away. And work that was done by Emily Petrov, who's now in Amsterdam, they did a number of experiments, and they came to the conclusion that these periton signals, these swept frequency radio pulses, they were actually coming from the observatory microwave. So when people were having lunch at the Parkes telescope, if they were impatient, they were heating up their hot dog and they opened the microwave before the magnetron in the center of the microwave was done, you're essentially opening this Faraday cage, which is the box of the microwave, and this radio emission can escape from this Faraday cage, and there's a very, very sensitive, very large radio telescope nearby, and you see this radio flash, and it's intrinsically swept frequency. So this is a question that someone was asking yesterday. So you have dispersion, which shows you that something has traveled through an ionized plasma, but imagine you have an emitter that also intrinsically sweeps in frequency. This can happen. There are emitters, man-made emitters that intrinsically sweep in frequency. Well, that could mimic dispersive delay. So you have to be very careful with this. But despite that, ongoing work with the Parkes telescope found a population of fast radio bursts. So there was ongoing survey with the Parkes telescope to look for radio pulsars. Parkes has been very successful at finding radio pulsars. Probably half the pulsars that have been found with the Parkes telescope. And in that data set, they found 4 examples of things that look similar to the Lorimer burst. And this is one of the nicest examples. Again, a dynamic spectrum. So you can see frequency versus time. You can see the beautiful sweep there. They determined, I think, just grab some chalk. Of course, one of the things you want to do is see how perfectly does this follow the expected dispersive delay. And I think they found that the frequency scaling of that dispersive sweep in this case, the index, so if you talk about time delay being proportional to frequency to some power, they found that in this case alpha was like 2.000 plus or minus 0.001 or something like that. So with such a high signal to noise and with such a large band, it's possible to do a pretty careful confirmation that the sweep in frequency matches what you would expect from interstellar and intergalactic dispersion. You'll also notice, and hopefully you still remember this from yesterday, this scattering effect. So there's a dispersive delay, meaning the signal arrives later at lower frequencies, but in the top right-hand inset of this plot, you can see that the pulse actually becomes wider as you go to lower frequencies as well, and it does so in an asymmetric way. You get this exponential scattering tail, and that also matched the frequency scaling that you would expect for Kolmogorov turbulence. So this means that the width of that scattering tail is going roughly as nu to the -4. It's becoming quite more scattered as a function of frequency, even across this relatively narrow band. So this was pretty exciting because this was a lot stronger evidence than we had before. All of these events appeared in one or adjacent pixels of this multi-beam camera on the Parkes telescope. People were still skeptical, though. People became quite a bit happier when, using the Arecibo telescope, we finally found an example of this phenomena using a telescope other than Parkes, using the Arecibo dish in Puerto Rico, which is a very, very large dish compared to Parkes. So this event is intrinsically much weaker than the one seen at Parkes because Arecibo is easily an order of magnitude more sensitive than Parkes. Again, the dynamic spectrum and the right-hand inset, you can see what the burst looks like when you de-disperse the data and add all the frequencies together. And you can see something that's a little bit odd about this signal, and that's the fact that it's quite bright at the highest frequencies, and then it disappears towards the lowest frequencies. And I'll come back to that later. We originally thought that, okay, maybe that's because the signal was coming in at a bit of an angle with respect to the axis of symmetry of the telescope, and that could mean that the sensitivity pattern of the telescope is quite complicated for these strange angles, and maybe that could be influencing the observed spectrum. Now we actually know that the source just has a very weird spectrum, and I'll explain some of our thinking as to why that's the case. So we have this population of fast radio bursts. As I showed you yesterday, this plot is trying to demonstrate observationally how these sources distinguish themselves from galactic pulsars. So again, what this graph shows is the maximum dispersion measure on the y-axis that you would expect from a model of the galactic electron density, and then the dispersion measure that's measured on the x-axis. And as I was saying yesterday, galactic sources should fall below that horizontal dashed line there. And we see that, in fact, the vast majority do. Obviously, there are some sources that pop out by a little bit. Could be that the model is not particularly precise in certain directions. We have this population of pulsars in the Magellanic Clouds, but then we have these fast radio burst sources, these open circles there that have much higher dispersion measures and also much higher dispersion measures than we would expect to be able to explain from the interstellar medium of our own galaxy. And in some cases, this is 30 or 40 times larger than what we expect from our own galaxy. So it's not a subtle difference with the model. This is really way, way off. So this is a current scoreboard. I told you a few minutes ago that there's a fast radio burst maybe every 10 seconds somewhere on the sky, but we've only found about 40 of them so far. And the number that's actually published is probably more like 25 or 30. There's a large number that have been found just in the last year by the ASCAP telescope in Australia. And this telescope has been enormously successful in finding fast radio bursts because it turns out that they can still be pretty bright. Obviously, the brighter ones are more rare, but what they've done with the ASCAP telescope, it's an interferometer like the Very Large Array or like Westerbork, and these individual dishes, they're only about 13 meters across, so they're pretty tiny dishes. But what you can do is you can operate the telescope in something called a fly's eye mode. So you can point each one of the telescopes, instead of using it as an interferometer, you can point each one of the telescopes in a different direction to cover a much larger area of sky. And each one of those telescopes that they're using also has a multi-pixel receiver. So it already has a very, very large field of view to start. So by covering hundreds of square degrees of sky with this telescope, even though they have very low sensitivity, they're still sensitive to very bright, very rare fast radio bursts. So a number of telescopes at low frequencies like LOFAR and the GBT operating at low frequencies, or the MWA in Australia, have failed to find any fast radio bursts, despite the fact that these telescopes also have enormous fields of view. And this could be because of scattering, which becomes very prevalent at low frequencies. It could also be from free absorption. If these sources are in environments that are very dense, maybe the radio signals are not getting out. And I'll come back to that a little bit later as well. But yeah, so there are a number of telescopes in the world that have found fast radio bursts now, which is very encouraging. And there are a number on the way. I'll show in a couple slides a number of observatories that are being built right now, which are going to have the computational power and the field of view to maybe start finding tens of fast radio burst sources every single day. The population is basically isotropic, which is what you would expect for an extragalactic source, so I won't dwell on this. And nicely, Emily Petrov has put together a nice catalog of the observed fast radio bursts. So if you want to look at the statistics of the population, if you want to even grab some raw data from some of these detections, similar to the data that I gave you guys yesterday, there's a nice online catalog that has plotting tools and has an archive of data where you can download some of the detected fast radio bursts. So like I said, there are a number of upcoming, what I would call fast radio burst factories that are on the way. We've really only scratched the surface given current radio telescopes. So a number of projects have started designing telescopes that are really more suited to just doing this, to just finding fast radio bursts. And in some cases, this has been done by repurposing other projects because people realize, oh, these other people have built a telescope that would actually work really well for finding fast radio bursts as well. And probably the best example of that is the CHIME telescope. The CHIME telescope is in Canada, not too far from where I grew up, actually. It's in Penticton in British Columbia. And what's interesting about CHIME is it has this really strange design. The telescope are these kind of half pipes. So there's 4 of those in a row, actually. So they're just these cylinders, half pipes, kind of like you would use for skateboarding. And along each one of these is a row of receivers. So there are a bunch of receivers, and I think each one of these half pipes has something like 256 of these receivers along it. And just like I was explaining yesterday for LOFAR and other interferometers, you can apply digital or analog delays to the signals received at each one of these receivers, and you can use that to point the telescope in different directions at the same time, because these 4 half pipes, these don't move at all. You steer the telescope just by steering these beams. Now, you can't steer the beams in this direction, so it's a transit telescope. You can actually only observe any part of the sky for about 10 minutes per day. It's within the field of view, but you can steer it and have angular resolution in this direction, in declination. And this is going to allow to create a field of view, which is kind of rectangular, but it's going to be something like 200 square degrees. And not only is there going to be a field of view of about 200 square degrees, because you have these various receivers here, you can actually divide this field of view into a bunch of spatial pixels. I think in total they're going to make 1024 pixels on the sky. So you can cover a huge area of sky, and if you detect a fast radio burst in one of these beams, you can also localize it with a precision of about an arc minute or so, which is not sufficient to do everything we want to do, but is pretty good start. So this telescope is going to be really interesting because it has the potential of finding tens of fast radio burst sources per day. So maybe even within a week, when it's fully operational, it will have produced more than we've had in the last 10 years or so. But this comes with a huge challenge, and this challenge is if you're forming all of these pixels on the sky, you have 1,000, you're looking in 1,000 directions at the same time, you're recording the data, every few tens of microseconds or so you have thousands and thousands of samples per second, and you have many frequency channels to correct for that dispersive delay. The data rates are absolutely insane. We're talking about terabits per second that need to be analyzed in real time, search for astrophysical signals, because you can't actually store the data that's coming from the telescope. All right, so the future is bright. But let's get back to the present. I'm not going to go through this whole laundry list. If you're really quite interested in this topic, obviously you can download the talk and look at this in detail. But one of the things that observers do is they think about, for a given signal, what is kind of the laundry list of things that we could possibly observe from this type of signal? What are all the different properties that we could observe, and how can we use them to understand the physics? So we talked yesterday about these different propagation effects, and things like dispersion measure and rotation measure are the types of properties that I'm talking about, but there's obviously much more. We can look at the spectrum, obviously, of the source, the pulse width, the scintillation properties. We can see if, in the case of a repeating source, whether there's a periodicity or not. We can try and associate a radio source with multi-wavelength companions. I mean, most of this stuff should be obvious to you, but if you really sit down and think about it carefully, you can write down quite a long list of things that we should be trying to extract from the data. And what have we observed so far? Well, we've observed pulse widths of about 30 microseconds to about 10 milliseconds or so a very wide range of pulse widths. When you have a pulse that's only 30 microseconds long, this constrains the size of the emitting region, right? Obviously, you can play with relativistic effects a little bit, but we're talking about emission regions that are quite small, kilometer scales or smaller. The dispersion measures that have been detected so far, if we take a simplistic model for how you convert a dispersion measure into a redshift, and typically people just use this simplistic equation, that redshift is about 1200 times the, this should be divided. A redshift of 1 is a dispersion measure of about 1200 or so. If you play this game, then, the dispersion measures that we've seen so far go from actually a few hundred up to a couple thousand. And this means that the redshifts that you infer from this go from quite small up to a pretty phenomenal redshift of about 2 or so. So these are these two sources at the extreme. We have one fast radio burst source that has quite a small dispersive delay. From this you infer a redshift of only about 0.05. But this is so much larger than what we would expect from our galaxy. We would expect only maybe about 30 units in this case from our own galaxy, that we're still pretty confident that this must be extragalactic in nature. But recently there's also been a source found with a dispersion measure of 2,600. And this implies, unless there's a bunch of dispersion measure that's local to the source, maybe it's in a very dense, very active region of the host galaxy. Maybe it's in a star formation region and behind some kind of H2 region or something like that. But if you take the dispersion measure at face value, then we're talking about a redshift of about 2 or so. So that's an enormous, enormous distance, right? We're talking about several gigaparsecs or so. You might ask, is the brightness, yeah, please.
So is it weird that it was at such a large dispersion measure and not scattered?
Yeah, so that's a very good question. So for pulsars in our own galaxy, you see a correlation which is it's pretty rough, pretty noisy correlation, but you see that the pulsars with higher dispersion measures typically are more highly scattered. They're traveling between more stuff. But the geometrical weighting for pulsars in our own galaxy is drastically different than what we have in the case of an FRB. There you're talking about a scatterer that's within our own galaxy, and it's something like halfway between the source and us. And here we're talking about scattering that's maybe happening in the host galaxy, and that means that the geometry is quite different. And the way you can draw that is that, say you have an FRB source here and you have an observer here, and the scattering screen is maybe halfway between for sources in our galaxy. So you can get a lot of scattering because rays can bend back and still come into the telescope. But if the scatterer is here, they've hardly diverged at all, and then they're coming back already. So the scattering cone, as we call it, is much smaller. Yeah. So that is one of the reasons also why people think that this is some circumstantial evidence that these sources are extragalactic in nature, because the large dispersion measure, if it was happening in our own galaxy, would suggest that the sources would be much more scattered. Great. So you could also ask, is there a correlation between the brightness of a given FRB and its redshift or its dispersion measure? And so far, not really. So that's what's shown in the top right-hand corner here. It does seem like the sources that have lower dispersion measures are maybe a little bit more bright, but it's a pretty messy, pretty scattered relationship at best. And this, I think, is not surprising at all. Yeah, I think this is not so surprising at all, because I don't think you should think of these things as standard candles. This is coherent emission, which is going to be highly beamed. So how that beam is directed towards us is going to play a very strong role in how bright the apparent brightness at Earth. So I think it's unlikely that we'll be able to use FRBs as standard candles, and I think any correlation of brightness with dispersion measure is going to be very, very messy. Well, I'll get into more detail about polarization measurements and rotation measurements, but I will point out one quite bizarre thing. Well, first of all, in terms of polarization, sometimes fast radio bursts show absolutely no polarization at all. Sometimes they show very strong circular polarization, and sometimes they show very strong linear polarization. So there's just a very homogeneous, or heterogeneous, I should say, picture when you look at the polarization of these bursts. But to be honest, that's the same for pulsars as well. So maybe it's not so surprising if the emission mechanism is not unlike that of pulsars. What's maybe more surprising to me, at least, is we can measure the rotation measures, so the amount of Faraday rotation towards a number of fast radio burst sources where it's been possible to record polarimetric data. And we see that 4 of these fast radio bursts have quite large Faraday rotations, so it suggests that they're in a pretty dense, highly magnetized environment, whereas 2 of them have very, very low rotation measures, which are consistent with just what you would expect from our own galaxy. So they appear to be in very clean environments. So it suggests maybe that they come from a different type of source. You can ask about multi-wavelength counterparts and whatnot. Kind of the best opportunity that we've had so far is from this repeating source. And I'm going to spend a good fraction of the lecture talking about this repeating fast radio burst source. For now, just know that one of these sources shows repeated bursts at the same dispersion measures, same sky location. But despite this, there are no contemporaneous optical X-ray or gamma ray flashes. So far, we've only seen these types of bursts in radio. And certainly, if there was a bright gamma ray or X-ray counterpart, if you just think about the event rate, if there really are tens of thousands, or at least thousands of fast radio bursts per day visible in the radio, the chances that that they all have an X-ray or gamma ray counterpart that would be easily detectable is very unlikely, right? Because otherwise we would have found this phenomena with other types of telescopes as well. Okay. So you can ask the question then, if there's one repeating source, and a lot of the other sources have been looked at for a very long time, people have stuck a telescope just staring at a particular sky position and waiting to see if it repeats. Is it possible that we've actually already detected two physically different types of fast radio burst sources? Maybe these signals don't all come from physically the same source. Maybe there are multiple types. This is possible, and I'll comment more about this during the lecture. If you look at the archive and all the theory papers, there must be at least 40 different kinds, because there's a very rich group of papers describing all of the possible ideas for where these sources could come from. And they need to take into account this huge implied event rate, right? So until recently, a lot of people have been trying to find more conservative galactic models. So people have been talking about maybe flare stars within our own galaxy. But given some of the recent insights from the repeating fast radio bursts, I think people are mostly focusing on extragalactic origins now. So I'm obviously not going to go through this list one by one, but I put this in here in case you download the lecture. This is a slide that I stole from Tony Pirro. He gave a nice talk in Aspen a couple of years ago where he was talking about all of the possible models. And these involve neutron stars in some cases. They involve neutron stars smashing into things in some cases as well. And they involve more exotic things. So if you want to kind of describe the different types of theories that people have proposed, there is certainly a whole class of theories that talk about isolated neutron stars that can be very young, highly spinning, highly magnetized, trying to extract either rotational or magnetic energy. I think there are also some models now trying to extract bursts that are powered by accretion. And these models are arguably a bit more conservative because they're just trying to take what we already know about pulsars and see if we can scale things up to get them to work at extragalactic scales. Andrei Belaborodov has worked on theories involving magnetars and magnetar bursts. But before the repeating source was found, there were a number of models that were cataclysmic in nature. So for instance, Heino Falco and Luciano Risola promoted a model in which you would have a hypermassive neutron star, so a neutron star that's actually more massive than the non-spinning equation of state could actually support, that's maybe formed in a merger event, spinning very rapidly, can support itself from collapse, and when the source finally slows down enough to collapse, then it produces a electric dipole, which can create a radio flash like we see. Compared to other models, these are pretty conservative because we also have people talking about axion stars. I'm not really quite sure on what axion stars are or how they form. Configurations in which you, for instance, have a planet which is very close to a highly magnetized neutron star and is actually passing through the magnetosphere of that neutron star, so something similar to what happens with Io and Jupiter, but then scaled up by many orders of magnitude. And people also talk about things like cosmic string cusps annihilating and all kinds of other more exotic theories. But you could also ask the question, of course, what good are these signals to anyone anyway? Obviously, if it's a very, very exotic process, that would be very interesting. But let's imagine that these sources are just neutron stars that are highly energetic and produce radio pulses at very large distances that we can still detect. Well, in a general sense, these sources are sites of extreme astrophysics. So like gamma ray bursts, I think we want to study these sources so that we can understand the extremes of the universe. So hopefully they can provide rich insights like gamma ray bursts have. It could be that they're a new type of astrophysical object, but for me, one of the most interesting aspects is, unlike gamma ray bursts, and like I've emphasized many, many times now, what we see in radio is not what was emitted in radio. Every signal that we're detecting with a radio telescope has undergone all kinds of propagation effects on its way to Earth. And that means, just like we've used pulsars as probes of the interstellar medium in our own galaxy, we've used it to probe scales of turbulence in our own galaxy, we've used it to detect the magnetic field of our own galaxy through Faraday rotation. Hopefully we can use these as beacons to study the intergalactic medium. So let's talk about this repeating source of fast radio bursts in a bit more detail. So this was found again with the Arecibo radio telescope, which is a telescope that is in this karst depression in Puerto Rico. So this is a natural limestone sinkhole in Puerto Rico where 60 years ago someone had the brilliant idea, let's fill the entire valley with a giant radio dish. This has been done more recently in China with the FAST telescope as well, which is even larger. And so that main dish is not moving. The platform above it is where the radio receivers and the focus of the telescope are located. And for many years now, we've been doing a survey for pulsars using this radio telescope. We've been surveying the galactic plane. So this is just a schematic of the spiral arms of our galaxy. And Arecibo can see an area of the galaxy which we call the inner galaxy. And all the pulsars that we've discovered are in blue. And we also look towards the anti-center of the galaxy. And there's not much galaxy left in that direction. You can see that there's just a Perseus arm, and beyond that there might be another outer spiral arm, but that's a bit uncertain. As you can see from these blue dots, these are discovered pulsars. You might ask the question, why are you even bothering spending time looking in the anti-center of the galaxy? There's not much there, and that is quite true. Turns out you can get data for free if you're piggybacking on someone else's experiment, and this is what we were doing. And this is how this Arecibo fast radio burst was discovered. So the source is actually in the galactic plane, but we do not think it's galactic. The reason it's in the galactic plane is because that's the only place we've been looking with Arecibo is in the galactic plane, so we, by definition, can't find anything outside the galactic plane. This is the burst itself again. If you try and understand the large dispersion measure of the source by looking in multi-wavelength data to see, maybe there's some kind of ionized H2 region in this direction, which is producing extra dispersion measure. Maybe this is some kind of galactic pulsar that's behind some extra dispersive material. Turns out there's just nothing in that direction of the galaxy, so you have a couple of H2 regions here, and the green circle is showing you the direction of this fast radio burst source, and there's just nothing going on in that direction. And conventional wisdom with fast radio bursts was that they don't repeat, so it was actually quite difficult to get more telescope time to reobserve this source because, well, what's the point of spending telescope time on a source that will never repeat? But we managed to get time anyway, and we detected a number of more bursts with additional observations. So each panel here is a separate burst from the source observed at a different time. And all of these bursts have, in this case, been corrected for dispersive delay. That's why the pulse is straight as a function of frequency. So they're all coming from the same direction on the sky, and they all have the same dispersive delay, so that's good. They must all be coming from the same source. But you can see that the spectrum, so how bright the signal is as a function of frequency, is quite drastically different between bursts. So for instance, if you look at the bottom, the last two bursts, bursts 10 and 11, those bursts came only a few minutes apart, but one of them becomes very bright at low frequencies, the other becomes very bright at high frequencies. So that's a bit of a mystery already, and it's a mystery I'll come back to in a bit. We're also able to detect the source with a different telescope, with the GBT, so it can't be any kind of local source of interference. We didn't really think it was anyway. And of course, this leads to the question, you know, if you have a repeating source, obviously it cannot be from a cataclysmic event. It's not from a one-time only explosion, right? So what is this source? Is it some kind of pulsar on steroids? Is it at a large distance? And how does it relate to the other fast radio burst sources? And to answer this question, what you need to do is you need to localize it. And this is what has really hampered the field up to now. Even if we start finding tens of fast radio bursts per day, if we don't localize them precisely, what we can do with them scientifically is still limited, unfortunately. So Arecibo also has a multi-pixel receiver, like the one, the 13 beam receiver I was telling you about with Parkes. In this case, there are only seven beams, seven pixels on the sky. And when we detected these repeat bursts, we were able to localize which sky direction the bursts were coming from. So that is indicated by those filled yellow circles. Those are positions on the sky where we saw the burst coming from. And unfortunately, those are the precision on the localization is still only at the arc minute level or so. So we could see that the source was following the sidereal rate, which is good. That means it must be an astronomical source. But you can only put a lower limit on the distance to the source if you have a position that is uncertain at the level of an arc minute. Turns out actually that if you localize the source to about an arc minute and you see that it's following the sidereal rate to about an arc minute precision, you can only say that the source must be more than, say, 100, 130 AU away. So we even started thinking about, okay, could this be one of the Voyager satellites? Could this still be a man-made signal, but coming from one of the Voyager satellites? Okay, so I'm going to take you through 3 papers which show the value of localization and which emphasize what we've learned about this source so far. So again, the Arecibo localization was insufficient to associate the source with any kind of host galaxy, so we had to use a very large array. It was natural to use a very large array because with an interferometric radio array, you can localize sources to a fraction of an arc second, so 2 orders of magnitude better localization. And I've illustrated that in this schematic here. So the Arecibo localization is illustrated by that large circle there. This is not in the direction of the Hubble Deep Field, obviously, but just for comparison, that is the size of the Hubble Deep Field there. And you can see within that area of sky, there are tons and tons and tons of galaxies. And the VLA localization that we're after then is comparable to that small circle there. That's what you need to detect the host galaxy. So we sat on this source for a good long time. And we made radio interferometric images of this area of sky. So those white circles are, again, where we detected it with the single-dish Arecibo telescope, where we saw bursts. And what's shown in the image, those are not bursts. That is persistent radio emission from this area of the sky. So you can see, for instance, in the bottom corner there, that's a radio galaxy with 2 lobes coming from the supermassive black hole at the center. And there's another active galaxy up there. And then there are a number of point sources. And what's nice is that the VLA has the ability to make these very high resolution images, but it has also developed the ability to record the cross correlations between different telescopes on millisecond timescales. And that's what you need to be able to detect a burst. And this succeeded. We were able to capture a burst with a VLA. This is now an image that's made not from many tens of hours of data. It's made from only 5 milliseconds of data. And you can see the location of the burst. It's at the cross between all of those lines. You might ask me, why does the image of the burst, why isn't it just a point source on the sky? Why does it have this kind of star shape to it? And that has to do with the shape of the Very Large Array itself. The telescope on the ground, as I was trying to explain yesterday, you only have high angular resolution in directions where you have a large distance between telescopes, and that means that in 5 milliseconds or so, that every point source will actually look like a star in this case. But we localized the source. It was within the region that we would have expected with Arecibo. This is after you clean out the response of the telescope, it is indeed a point source, and that's what the dynamic spectrum looks like. So again, we see this dispersive sweep. So not only did we see a burst that had a very specific position on the sky, it also had the same dispersion measure, so it's nominally at the same distance, so it must be the same thing. What was interesting is that in doing this, having this precise localization, we were able to go to optical data, able to see what is there in archival Keck data, and we were able to take new Gemini data. So the archival Keck data is shown in this figure here. It's the blue data in the inset there, and right at the position of the radio localization, there's an optical source, a very tiny little optical source. So it wasn't even so clear at the time whether it was a galaxy or whether it was a star. And just to make the point, I think a number of people here have worked in GRBs before. This is not an afterglow that we're looking at. We're making a real-time detection of a burst from the source, and we're localizing it in real time. This is fundamentally different than other techniques that have been used to localize GRBs or to try and localize other fast radio bursts, where, for instance, if you see a fast radio burst, then you start taking multi-wavelength data of that field and you look for a source that's fading, and then you say, well, it seems statistically like that fading source must be associated with the burst that we saw. That's not what we're doing here. We're doing a direct localization. So we have a precise localization. It was precise to a fraction of an arc second, but we wanted to go even further. We wanted to localize the source even more precisely. And this was done using the European VLBI network. So the European VLBI network is a sometimes operational. It doesn't operate 24/7. For some parts of the year, large radio telescopes in the world send their data to Dwingelo in the Netherlands. And that data is correlated. So the cross correlations between telescopes are stored. And because these telescopes actually span the entire planet, you can have even higher angular resolution than you can have using a telescope like the VLA. And this is obviously an artist's impression, but that's when the actual burst that was detected, that's how the real data looks like. And why would you want to zoom in even further? Because I told you we have this optical counterpart, and I'll come back to that in a second, what that optical counterpart actually turns out to be. But why would we want to zoom in even farther? Well, the reason why you want to zoom in even farther is, imagine that optical source is a host galaxy. We want to know what part of the host galaxy is the source coming from. So again, we use the European VLBI network. These are some of the dishes. I can just skip through this. This is probably also unnecessary. There we go. And this is what the image actually looks like. So we captured a burst with the European VLBI network, and the way that image looks when you don't deconvolve the response of the telescope is what's shown by this so-called dirty image. So in this experiment, one only has something like 6, 7, or 8 telescopes available. And in the same way I was showing you that star shape for the VLA, we get similar kind of ringing, we call them side lobes, when you use a limited number of radio telescopes. So once you clean that response to the telescope out, you get this clean image, and that's a localization of this fast radio burst that was detected with the European VLBI network. And if you look at the scales now, from left to right is about 40, well, in total is about 80 milli-arcseconds. So we were able to localize the source to about 10 milli-arcsecond precision, so very, very, very high precision. And what we found is that the bursts are consistent with coming from the same direction as a persistent source of radio emission. So I told you already that we have radio bursts, I told you already that we have an optical counterpart, but it turns out that there's also a persistent radio source, a radio source that isn't bursting, that's just constantly there. And that source, which is shown in this color map here, the kind of bright yellow area at the center, that source is compact. And that is radio astronomer jargon for saying that it is unresolved, even using telescopes that are spread around the entire globe. Right? So this source has to be absolutely tiny on the sky. And let's imagine now that the dispersion measure that we have tells us the distance to the source, and maybe the distance is about a gigaparsec or so. If the source is at a gigaparsec, then we can limit the offset from the position of where the bursts are coming to the position of this persistent radio emission to only 40 parsecs. So that's a pretty small angular scale. And we can also say that that persistent source of radio emission has to be smaller than about a parsec or so. So it has to actually even be smaller than the Crab Nebula. Very, very tiny. But now the clincher, the real clincher, is getting an independent determination of redshift. And this was done with the Gemini telescope, because you need to determine what is the nature of this optical emission that's associated with the position of the radio burst. It's quite challenging because this optical emission is 25th magnitude, so that's just kind of barely detectable, even for a fairly large telescope like Keck or Gemini. And what you ideally want to do is do spectroscopy, right? You want to determine a redshift by having spectral lines that can tell you what the redshift is. So this didn't seem like it was going to work, but in the end it did actually work. And this is the Gemini spectrum from very long integration with Gemini North. And the line that I would focus on here is the host galaxy line, so the dark blue line. What you can see as a function of wavelength, now optical light from about 5,000 to 8,000 angstroms or so, you can see that there's an extremely faint continuum, basically no continuum at all, but there are a number of spectral lines. So we have H alpha, we have some silicon lines, and we have some oxygen lines, and hydrogen beta as well. And what this tells us, how you interpret this, is this very weak continuum tells you that if this is a galaxy, there are very few stars. And those strong emission lines, though, they tell you that there must be a high star formation rate. There's a high rate of ionization. And if you take the rest wavelengths of these lines and compare them to what we've actually observed, you find the redshift, and the redshift comes out at 0.2. It's actually 0.193, something like that. So this is great. This gives an independent measure of the distance, a far more accurate measure of the distance, which basically agrees, roughly speaking, with the dispersion measure. Using a dispersion measure for a distance estimate has the unfortunate issue that we need to guess at how much dispersion measure is coming from the host galaxy, and that's quite uncertain. Whereas here we get the redshift directly. And this sets the energy scale of the bursts. So now that we know the distance and we know how bright the observed bursts are, we know what the energy scale is. And it's quite large, it's 10 to the 40 ergs per second or so. The optical emission is coming from star formation. It's not coming from an AGN. And if we talk about trying to localize the source within the galaxy, we first took images with Gemini, but then zoomed in further with Hubble. And what we found, and this is why it was very useful to have very long baseline interferometry, this is a tiny dwarf galaxy, it turns out. So that ellipse is showing you the emission from this host galaxy. And within this host galaxy, what you can resolve if you get a Hubble image is that there's a knot of star formation that is shown in the upper left-hand side there. And that knot of star formation in this galaxy, which is like less than an arc second across or so. This is a tiny little galaxy because it's a dwarf galaxy at a very large distance. The localization that we have from the VLA and from the EVN puts the position of the bursts right on top of that star formation region. So not only do we know that these bursts are coming from this host galaxy, and not only do we know the distance, we also know that they're coming from a region of star formation within that galaxy, which is highly suggestive, right? It turns out that this is a very low metallicity galaxy. It's a galaxy that, interestingly, is the type of galaxy that is also commonly associated with superluminous supernovae and with long gamma ray bursts. So in finding this galaxy, not only have we figured out that the source of the repeated bursts is associated with a region of star formation, suggesting that it's maybe a very young source, not only have we figured out the distance, but the type of galaxy as well is the type of galaxy that has been associated with other types of astrophysical transients. So what does that mean? Am I saying, for instance, that these bursts are coming from long gamma ray bursts? Are they coming from superluminous supernovae? Well, what I actually mean when I say this is imagine that this type of galaxy can form very, very massive stars that when they collapse and become neutron stars will produce a long gamma ray burst or a superluminous supernova. What's left afterwards could also be a very extreme neutron star, which is then an engine that is capable of producing fast radio bursts. So I'm suggesting that there's potentially an evolutionary link between these cataclysmic events, long gamma ray bursts and superluminous supernovae, and now this pseudo-persistent, long-lived transient, which is an engine that was created by these extreme transient events. So I'm going to try and wrap up in the next 15 minutes or so, give you some more recent insights about this source, and then try and wrap the story together in terms of FRBs in general. Obviously, once you have localization, you try and hit the source with every large telescope you possibly can. And that's an advantage of having a repeating source is that you can wait for it to do something interesting again and hopefully capture it in other wave bands. So for instance, we have tried extensively with Chandra and with XMM Newton to detect X-ray flashes or some kind of persistent X-ray source, and there's just nothing there. So unfortunately, this is only lightly constraining on magnetar models, because if you predict how bright this source should be, if it was a magnetar at this distance, it's really at the limit of what we can actually probe with XMM or with Chandra. Similarly, we have not found any optical flashes, and similarly, we have not found any gamma ray flashes. So in the absence of some kind of prompt or persistent multi-wavelength counterpart, how are you going to try and figure out what the source actually is? Well, you're stuck with just the radio bursts themselves. So we really have to maximize what we can get out of the properties of the radio burst. So this means, for instance, looking at the polarimetric properties of the burst, and it means looking at the time frequency structure of the burst. So not just that dispersive delay, but let's start looking at the pulses and the pulse shapes in more detail. And a nice example of this was the first fast radio burst that was found with the Green Bank telescope. What was interesting at the time, this was a few years back, was when they detected this particular fast radio burst source, they also detected Faraday rotation. So what's shown in the black curve there is the total intensity of the burst, so the total radio brightness of the burst. And those other colored lines, those are plotting the Stokes parameters, the polarimetric properties of the signal. And you can combine those to get a rotation measure. That's shown on the left-hand side here. So that wiggle of the Stokes parameters with frequency is showing you how the linear polarization angle is changing with frequency. This allows you to measure the rotation measure, and under certain assumptions for the amount of dispersive material that's associated with that, you can also calculate a magnetic field. And this was used to argue, well, this source seems to be coming from an area which is particularly highly magnetized. So that suggested this particular fast radio burst source was not in the outskirts of some kind of elliptical galaxy in a very clean environment that you might expect for a neutron star merger or something like that. So this is a non-repeating source which has a fairly large rotation measure, suggesting it's in a fairly magnetized environment. This prompted us to look at in more detail to try and find rotation measure from this repeating source. And these are the data that I gave you yesterday, and I've mentioned this yesterday and shown this plot yesterday. So again, this plot is just showing in the top two panels the Stokes parameters, how they vary with frequency as lambda squared. This allowed us to determine the rotation measure for the source, and it turns out that the rotation measure is absolutely enormous. In the rest frame of the galaxy, so you need to correct for redshift as well, it's about 140,000 once you correct for redshift. And if you plot, for instance, the dispersion measure here on the right-hand plot, if you plot dispersion measure versus rotation measure for galactic pulsars, those are all the black dots, you can see that there is a rough correlation between dispersion measure and rotation measure, but a typical galactic pulsar has a rotation measure of, say, 100 or 1,000 or something like that. A number of FRBs have been found with low rotation measures. The only pulsars in our galaxy where we've seen very, very high rotation measures, those are the sources where the pulsar name is actually given in the top right-hand corner there. Those sources are all near the galactic center. And in fact, that red dot in the very top right-hand corner, that is the galactic center magnetar. So this is a radio-emitting magnetar that was found a few years ago, very, very close to Sagittarius star. And it has a rotation measure of something like 70,000 or so, which is absolutely enormous compared to a normal pulsar. And it has been suggested that that enormous rotation measure is coming from the fact that it's actually within the accretion flow around Sagittarius star. Could well be. And that is comparable to within a factor of 2 to the rotation measure that we're finding for this fast radio burst source. So that led us to actually speculate that, well, maybe this repeating fast radio burst source is also in a galactic center-like environment. In fact, if you look at this persistent radio source, which is compact, in many ways it actually looks like an AGN. So maybe this fast radio burst source is not necessarily coming from an AGN, but maybe it's coming from a neutron star that's in the close vicinity of an AGN. Why that matters, I mean, theorists can speculate ad infinitum as to why that might matter or not. But typically, in a galactic center environment, there is a lot of star formation. So it could just be that the source is in an area of active star formation, which is also a galactic center-like environment. But one of the things that you can do is you can use equipartition of magnetic energy to calculate, what the physical properties of this type of environment are, and see what type of physical scenarios that's consistent with. So these different panels are plotting electron density versus size of the region. You have some constraints given in red from free absorption, and the different panels are plotting different temperatures as well. And you can see what regions of this parameter space are consistent with the source that we actually have. I won't describe everything in these plots because it's a little bit complicated. You need to look at this for a few minutes to really start understanding what all the lines mean and whatnot. But the take-home message from this, I would say, is that indeed, given the measured magnetic field strength and given constraints on the size of the source that we have from VLBI measurements, we can say that the source is actually consistent with being in a galactic center type environment around a massive black hole, but it could also be in a very powerful nebula. It could also be in something like a very young version of the Crab Nebula. So imagine that persistent radio source is a very, very young version of the Crab Nebula, or maybe it's a magnetar wind nebula or something like that. That could also, in principle, produce the observed rotation measure that we're seeing. I would keep in mind, though, that persistent radio source is enormously luminous. That source is about 1 million times brighter than the Crab Nebula. So I was telling some people at lunch that if you were to put that source in our own galaxy, if the source lived in our own galaxy, it would be brighter than the sun in radio at the distance of the Crab pulsar. Okay, so kind of the last thing that I'll mention before I conclude is, so I said that we want to look at the shapes of the bursts. We want to look at how they change in time and frequency in a more detailed way, let's say. So these are, again, dynamic spectra of the bursts, so frequency versus time, and I've corrected for dispersion measure already. And after you correct for dispersion measure, there's still a lot of weird stuff going on. And what you see is that the bursts are composed of individual peaks, so we can resolve them in time and find individual peaks. But we also find that each one of those peaks is kind of spectrally confined. It peaks at a certain frequency, and that frequency seems to drift as a function of time, so it seems to drift to lower frequencies. This is really bizarre. Pulsars do not do this. And we found several examples of these bizarre bursts. Whenever we have high enough signal to noise and high enough time resolution, we seem to see this effect. And one of the options here, which I'll come back to, I have a couple slides, is that this could be induced by material around the source as opposed to being intrinsic to the emission process. Now, interestingly, you're asking probably, yeah, but is this source related to the other fast radio bursts we've seen? Well, interestingly, several of the other fast radio burst sources have also shown multi-peak bursts. So those are highlighted by the green shades there, which have very similar shapes to this repeating fast radio burst source. And it's been argued that even in a cataclysmic model, you could maybe have a few radio peaks as opposed to just a single delta function. But any kind of impulsive radio signal with multiple peaks suggests that maybe the mechanism is not cataclysmic. This was just for a fun slide showing that you can also visualize this data by 3D printing it. So this is what some of these bursts look like when you make a 3D print of them. So it's frequency versus time versus brightness. It looks like a bunch of mountain peaks, kind of. So where are these weird shapes coming from in the bursts? Well, our favorite theory right now is that this is coming from plasma lensing. So the idea is that maybe in the local environment of the source, there is high density plasma that can act like a lens and can produce caustics in the plane of the observer. So the way this is illustrated in one of our papers is, so imagine you just have some plane parallel waves that are coming along, and imagine you have a lens that just has a Gaussian density profile. That's an oversimplification, but just imagine that. Then just using simple ray optics, you can trace where each one of those rays is going to end up at the bottom there, which is the plane of the observer. So for a certain offset with respect to the source, these rays can pile up. Just like a wine glass where light is passing through a wine glass, you can get certain areas with caustics. These are caustic points produced by this lens, and they can produce multiple images. So they can produce repeats of the same pulse, apparently. But most interestingly, they can actually boost the signal by an order of magnitude or maybe even 2 orders of magnitude in brightness. So this could go away to a ways to explaining why this source is so readily detectable despite the fact that it's so far away. And recently there was a paper that was out showing plasma lensing in the Black Widow pulsar as well. So we know that this actually happens. Okay, I'm going to end in the next few minutes or so. Is that okay? 2 minutes, yeah? Okay, so let me just summarize what I've told you about the repeating fast radio burst source. It requires a source that can survive the very energetic events that produce the bursts themselves. So it's not a cataclysmic event. It's an engine that can continue pumping out these very bright bursts. And we know that they're very bright bursts because we've localized it to a star-forming region in a dwarf galaxy at a gigaparsec or so. Now it's persistent with this, or it's consistent with this persistent radio source, and we think that that radio source could be a very, very luminous nebula, like the Crab Nebula, or maybe an AGN. We have the energy scale of the burst now, 10 to the 40 ergs per second, and through Faraday rotation, we know that it inhabits an extremely magnetized environment as well. Now, the main thing that we're working on now is trying to measure the spectrotemporal properties of the burst, so the brightness of the burst as a function of frequency and time, to figure out what kind of role lensing is playing. So I think we need to end here. If you download the slides, then you can look at some of the extra slides I have just about some of the open questions in the field still. And I've also provided a couple overview slides that link to some of the important papers in the field. So kind of a timeline of developments in the field and important papers. That was it. Okay, so thank you. Yeah, it ended anyway. Are you okay?
For do you think eventually we'll have an all-sky radio?
Well, it's the parameters of any instrument are going to be sensitivity, field of view, time resolution, frequency, and with a limited budget, you always need to make trade-offs in what you actually build. So we'll always have telescopes that have limited sensitivity if they're looking at the whole sky, and telescopes that are more sensitive if they're looking at a smaller fraction of the sky. But you need to get just above some kind of threshold, right? If there's an astrophysical phenomena where if you have a minimum sensitivity you can detect it, then maybe you want to immediately go all sky then. And people are definitely thinking about how could you make an all sky fast radio burst monitor? Because if you want to do cosmology with fast radio bursts, then you want to be detecting thousands of them and localizing them.
It seems like if there are two like progenitors, like a repeating one and not a repeating, it seems like you need an all sky survey to find those, to be able to determine what's happening when they don't.
Yeah, well, critical to that is not just detecting them, it's localizing them. So people are working towards localizing them in real time when they're discovered. And in my mind, it would be much better to find 2 or 3 of them where you just localize them immediately and you figure out what the host galaxy is and the environment is. That would be much more valuable than finding hundreds of them where you have no idea where they're coming from. Yeah?
I actually have several questions, but I can start with one. This repeating one, is it on a, is the period constant, or is it?
Yeah, we've been looking for periodicity, but we have not seen any periodicity. Yeah, or you're referring more to the activity level. And the activity, is that what you're referring to? So there are certainly periods of time where bursts are more easily detectable, and periods where you go many months and you don't see anything at all. Yeah. And in the periods where it's very easily detectable, we've looked at the spacing between bursts to see if there's some kind of underlying periodicity, but we haven't found anything.
Are these bursts only going to be detected in radio, or could they be detected in other bands?
Well, we've tried, at times in which we've detected radio bursts, we've had commensal X-ray data and commensal gamma ray data and optical data as well, and not seen anything in those other bands. But that doesn't, like I said before, that doesn't really surprise me, because if the event rate is this high, then we would have found this type of object in other wave bands already. I mean, if Chandra does not have a very large field of view, but still, if there were thousands and thousands of X-ray flashes per day, I'd imagine that in the archive you would be able to find some of these events. Yeah. You had a question as well?
Yeah, a couple of questions. One, just how cooperative is SETI, for example? Do they provide their information to?
Yeah, SETI is very cooperative. I work with a lot of those people from the Breakthrough Listen team because, I mean, their primary goal is to search for SETI, right? But in doing so, they've built these beautiful, beautiful data recorders, very, very wide band. They can record the data with very high precision because they can actually get the raw voltages. So you have Nyquist sampled data, and some of the plots that I show actually include what I would call SETI data, because they have money to look for extraterrestrial signals, but they're also allowed to look at things that are called exotica. So they're also allowed to look at just astronomical mysteries as well. So they've been helping us quite a bit.
My other question, let's say, for example, radio waves that come from Earth, right? And we talk about things like dispersion measure, scattering, rotation measure.
Yeah.
How far would somebody be able to detect our signals?
Oh, that's a very good question as well, yeah. I think, I remember from a SETI paper that the largest radar on Earth, which is called the Space Fence or something like that, it's some American military radar, I think it would be detectable at only 50 parsecs or so. So the volume in which we can detect radio signals from technology like ours is absolutely tiny. I think what they're really hoping for is that someone sends a purposeful signal, right? Because if you can confine a message to a very narrow range of frequencies and you beam it in a very specific direction, then it can go much farther. You can detect something much further away. But if you're just talking about things that we make accidentally, the horizon is very small. Yeah. There's not too many stars and planets within a few tens of parsecs. Yeah.
For the case of the recurring bursts, the recurring fast radio bursts, did you notice any correlation between the waiting time and the amplitude?
And the amplitude? No, we didn't actually. That's a good question as well. One of my students, I don't have it in my presentation, but one of my students made a plot like that, and it's not obvious that the waiting time is longer for brighter bursts.
No, the opposite.
And not the opposite either. It's just pretty random. But it's beamed coherent emission as well, right? It's not like a type 1 X-ray burst where you think, oh, we need to wait a long time for material to accumulate before it goes off again. Yeah.
I've heard people that are working on FRBs say that it might be a synchrotron maser that is causing it.
Yeah, that's one of the theories, yeah.
What is the reason to believe this, except that it's only in radio?
I think one of the reasons is you can get a very, very high brightness temperature, so you can, with not so much energy, produce a detectable signal. One of the other reasons is some of these bursts seem to have very narrow band spectral features, which I would argue is maybe from this lensing effect, which also varies very quickly with frequency. But it could be that it's related to the characteristic frequency of emission, that it's an intrinsic process because it's a cyclotron maser, for instance. But my understanding, I guess Sasha knows better than I do, I don't think a synchrotron maser has actually ever been observed in astrophysics in a convincing way, right?